All right, great. Thanks so much, Ricardo, for the great talk. I'm Tyler Hayes. I'm a current research scientist at Neighbor Labs Europe, and I'll be talking about dynamic adaptation through lifelong and open world learning. So let's start off by talking a little bit about dynamic adaptation desire data. From a human perspective, we're able to continuously learn over time. We can identify and learn from unknown objects and environments, and we can also identify and learn from difficult or anomalous examples. This correlates with three subjects in the machine learning literature, so namely lifelong continual learning, open world learning, and active learning, which are the three specific topics I'll be covering into today's tutorial. So let's start off by talking a bit about the supervised machine learning paradigm. We're all very familiar with this. We give a data set and we split it into a training and a testing partition. They often come from the same underlying data distribution. I then train my favorite machine learning system offline on a static training set. If the performance on my test set looks good, then I can deploy. But the problem with this setting in practice is that if we receive more data or we receive more data from outside of that training distribution, we have some problems. So in lifelong learning, we're looking to address these problems by updating a network with new data over time. This mostly matches how the data is being received in the natural world, right? The world around us, it's constantly evolving and changing. It's not independent and identically distributed. Maybe we have some type of temporal correlation between the different frames within the world. So we need to be able to make agents that are able to adapt to these evolving and changing conditions. You might be asking yourself, well, can't I just naively fine-tune my neural network on the new data? And this comes to the problem that Ricardo mentioned in his last talk about catastrophic forgetting. So basically, if I naively get some new data and I just update my network using traditional gradient descent updates on that new data, the problem is my network abruptly loses the ability to perform well on previous tasks. On the right, I'm showing you a figure of doing this, what we call incremental class learning, where basically from the Cub 200 bird data set, the agent is learning one bird class at a time. And you can see in orange is just a standard MLP feed-forward neural network. And if I just naively update it on the new data, you can basically see that performance is dropping to chance, right? So basically, it's forgetting anything it knew about the previous bird classes in favor of only performing well on one new bird class. If we use some of the continual learning mechanisms that I'll talk about in a little bit, you can get performance that's closer to like this green or this blue curve. So why does catastrophic forgetting actually happen? This is known as what is the stability plasticity dilemma. Basically, my network needs to maintain stability in its weights to preserve previous information, right? If I want to perform well on prior tasks, I need to preserve what's the information that's in those weights. But if I preserve it too much and I totally freeze those weights, I don't have the ability to adapt the network to new data as it becomes available. So I still need some plasticity in those weights to be able to acquire new knowledge. So basically, to overcome catastrophic forgetting, we have to maintain some type of balance between the stability of remembering old things, but also the plasticity to be able to acquire new information. So another solution could instead be instead of naively fine-tuning on only new data, what happens if I do what I call cumulative replay? So cumulative replay is basically, let's take all of the data that the network has seen before, we take our new data, we concatenate them together, and now we update the network on this new concatenated data set that contains all old and all new data. This is great. It solves the catastrophic forgetting problem. In the right, you're seeing a plot that's basically in black, the cumulative replay performance with respect to an offline trained model on all of the data, right? This is overcoming forgetting. It's achieving nearly 100% of the offline performer's performance, but there's some problems that you can imagine come with this. The first one is that it doesn't scale, right? This is super expensive, especially if I'm training on a super large data set. Having to store all of that memory in some type of database or something like this is really expensive. And maybe it's even prohibited. What if I'm dealing with some type of medical data and I just, for privacy reasons, can't store that data for an extended period of time? This is going to be a problem. It's also not suitable for resource-constrained applications. If you're dealing with a robotic agent or something that you don't want to connect to a server to have to access all of that data, we need methods that are able to update in real time. If you care about biology and making your methods more biologically plausible, this also isn't really matching how humans and animals learn, right? It's highly unlikely that in our brains, we're storing a copy of every single experience that we've seen throughout our entire lives, concatenating them all together with new experiences and then updating. Another thing that I don't really like about this approach is that you can't transfer knowledge, right? So if the network has learned something useful because there's a lot of very similar semantic concepts in the world, we're not utilizing that semantic similarity if we're just retraining with all of that data again, right? Wouldn't it be nice if I've seen a bunch of cat breeds in the past and I see some new cat breed that I could just transfer some of those common features? So this is another motivation for not using this solution. So if I haven't motivated you already, there's some other reasons that perhaps maybe you're interested in studying lifelong or continual learning. From a basic research perspective, we could study how to make more efficient learning algorithms, right? So you could take your favorite large language model these days. It probably took several weeks or maybe even months or years to train. And if I get some new data, likely we're just gonna keep updating with all of the old and all of the new data. But wouldn't it be nice if I had some methods that could just focus on adapting only the parts of the network I needed without having catastrophic forgetting actually happen? I also think from a basic research perspective, it's interesting to think about these transfer questions, right? Like, how do we make the most transferable learning algorithms? How can we make use of these semantic similarities among concepts in the natural world? More than this, it can also enable some new applications. So one specific application that might be really interesting is on-device learning, right? So if I have these efficient transferable learning algorithms and they don't require much compute and memory, that I can deploy it directly on a device. This means I can operate in cloud, where no cloud computing or internet-deprived locations, right? So we could deploy these actual learning algorithms on some on-device hardware. So things you can think about are like AR, VR headsets, right? Localizing to the actual environment in my home, or even making customization, right? So maybe I have my smartphone that's adapting to my speech over time. Maybe you like this, maybe you don't, but it's an interesting thing to start thinking about. So let's give a formal definition to what I mean when I say we're going to study lifelong learning. So our goal is to be able to train systems that can accumulate and refine their knowledge over time from one or more domains to imitate human learning. And the two major challenges of this are overcoming catastrophic forgetting and enabling transfer to learn new information better and perhaps more quickly with fewer examples. So we have a couple of considerations. We want to be able to learn and recall new information immediately. This is basically eliminating that cumulative replay solution I mentioned earlier of just storing everything in the past. We want to be able to learn data in any order without catastrophic forgetting. So I think one common thing that's done in the literature these days is learning classes one at a time. So class incremental learning. But a lot of algorithms are designed only to work in this class incremental learning setting. And in a natural environment, this is highly unrealistic. It's not like I'm going to see dogs and then I'm going to learn cats and I'm never going to see a dog again. So we really want to balance these two extremes, right? So we really want to be able to test our agents in many different scenarios, ones where maybe classes aren't seen again, maybe where they are seen again, and everything in between. We'd also like to be able to study transfer of learned representations for learning efficiency, right? So being able to learn from very few examples due to the semantic similarities. It's also interesting to consider learning using limited memory and compute overhead. So considering things like how fast is it to store my data? How fast is it to access my data? What is the actual processing time for updating on that data? And the final thing is being able to scale to what I call large-scale high-dimensional problems. We don't want to be just evaluating these learning algorithms for our favorite conference on things like MNIST, right? They're probably not going to scale. But more than that, we need to start thinking about more realistic benchmarks, right? Maybe we have some video data streams. Maybe we have more challenging multimodal data streams where we have visual and audio inputs. So I think it's really important to consider all of these various different things as we start moving into the lifelong learning literature. So now that we've kind of given some motivation to the problem, let's talk a bit about how this is actually set up when you pick up your favorite paper. So the first setting that people often study is what I call incremental batch learning. So basically in incremental batch learning, you take a data set, you break it up into several batches. Here I've shown batch A, which is cat images, and batch B, which is dog images. At each time step, the learner receives an entire batch of data. So it will receive all of these cat images. It can then spend time looping and epoching over that data to learn it before it's evaluated at the end of the training cycle, right? So it would be evaluated once after learning a big batch of cat images. This might be relevant for applications where you have more memory and compute available. I say this because basically you have to queue up an entire batch of data before learning. You also have to wait for the learning algorithm to spend time batching over and learning this data. So if you have more memory and compute available, you're likely going to get higher performance doing this, but it might be a bit slower. You also can't get immediate inferences, right? So I mentioned that you evaluate once at the end of the learning cycle, but what happens if I just want to learn one new dog image and I don't want to have to learn an entire batch of new dog images, right? That's not necessarily a possibility in this setting. And if you have batch processing available to you, maybe this makes sense. If I have 10 GPUs to deploy at the same time, maybe I should just batch my data across the 10 GPUs and use it. On the flip side, we have what is known as streaming learning. Sometimes literature calls this online continual learning. There's a couple of different names. So sometimes you have to read about those specific procedure within the paper you're looking at. But in this setting, we're thinking more about the immediate processing. This is probably going to be more useful for applications where you're looking to deploy something on device or you want very rapid updates and inferences, right? So here you can see we've still organized our data in a similar way. We're learning cat images and then we're learning dog images, just for the sake of this example. At each time step, the learner is receiving just one new example, it learns it, and then it can be evaluated immediately after, right? So instead of queuing up a big batch and looping through it, we're just processing those examples one at a time. So again, this is relevant for applications where you maybe have more limited memory and compute. You can think of those more like on-device applications where you need immediate update and inference. Another thing that often happens, and I think that Masi and Ashwarya are going to talk a lot more about pre-training much later in this tutorial, but you could think about doing pre-training before doing continual learning. So maybe I want to initialize my features and my network to something useful, and then just do a little bit of continual updating on top of that. This is also a possibility where we could kind of mix some static adaptation approaches with dynamic adaptation approaches. I'm not going to spend much time on this, as you'll have 2 full tutorials on that a little bit later. You might be thinking to yourself that this sounds very, very similar to several other related fields that you've heard about in the past, and it actually is, right? So I really like this graphic from this paper that was published in TPAMI 2021, where basically on the left, you're seeing what the standard supervised learning scenario looks like. So we have a distinct training time and a distinct testing time, right? This is also related to multitask learning, right? So we break things into tasks. But the difference here is where all of that task information is being learned at the same time. So instead of learning task 1 and then learning task 2, etc., you're learning task 1, 2, and 3 all at the same time. It's also related to transfer learning, right? So I pre-train my neural network, and then I want to fine-tune it on my favorite downstream application. But the difference with transfer learning is usually we only care about performance on the downstream application. If I pre-train on an ImageNet and now I'm doing downstream airplane prediction, I only care about airplane predictions later on. But what happens if I also want to remember those classes from ImageNet? That's why we need to do continual learning. I think Ricardo covered a little bit about domain adaptation, meta learning, being able to learn the best policy for updating my network, and then also online learning. So in the online literature, we often only care about updating one sample at a time, but again, we don't care about previous knowledge. So we really don't care about this catastrophic forgetting problem. We only care about updating one sample at a time. So now that we've kind of seen how we formulate the problem, let's talk a little bit about some of the approaches you can take to actually perform continual learning. So there's 3 major ways to distinguish approaches to overcome catastrophic forgetting. The first is regularization based, right? So I could add some type of regularization loss to my full loss to regularize my parameters or my features such that they don't change too much, right? So I have some type of input-output relationship between my data, and I would like to be able to preserve that. This is basically targeting that stability axis of the stability plasticity dilemma that I mentioned much earlier. Another approach is called rehearsal or replay. You'll kind of seen these used synonymously in the literature. And this is inspired by how we as humans are actually performing the overcoming catastrophic forgetting problem, right? So maybe I have some type of experience replay buffer where I can either store explicit samples from the past or have some type of generative model that's able to replicate me examples from the past. I can then mix those with new examples and then update my network. And the third class is architectural. So basically you could imagine having some type of task mask that masks off parameters so that I don't touch them when I'm updating on new data, or I could even just expand my network's capacity over time to accommodate new data. I think that if you're interested in learning a lot more about the specific approaches for these three classes of methods, there's a really nice graphic and citations in this paper by Martin Munt that was published in Neural Networks 2023, where you can kind of see the breakdown of the various methods and look at what the current state of the art is. Of course, when you're considering, should I use a regularization method or should I use a replay method, there's different trade-offs depending on your particular application, right? So you can see in this graphic, we have replay methods at the top, regularization-based methods, and then parameter isolation-based or architectural methods at the bottom. And you can kind of see how much memory and compute they require. Are they task agnostic, or do they require some type of indicator about what the actual task I'm evaluating on at test time is? And do we have privacy issues, right? So in practice, replay-based methods have really great performance, but they come at the cost of requiring more memory and compute and maybe have privacy issues. So depending on the particular application that you're thinking about, maybe you need to start considering some of these trade-offs. So let's talk a little bit about some of the setups and what are the common data sets that are used in literature, right? So the first is some variant of MNIST, right? I break it up where tasks are learning 2 digits at a time, we update, and then we evaluate on all 10 digits. The problem with this is that algorithms that work well on MNIST usually don't scale up to natural image data sets. However, I still point this out because a lot of people are still publishing on this data set even today. So it's something to at least be aware of that exists. I argue it's a little bit more realistic to start moving to things like incremental ImageNet, right? So we basically take the 1,000 classes of ImageNet, we maybe break them up into groups of classes or learn one class at a time over time. The thing is that this data set's super large and it's great. It has 1,000 classes, high resolution images, but maybe it's not necessarily super realistic due to the missing temporal order or temporal aspect of this, right? So maybe for continual learning, it's more realistic to start thinking a bit more about video benchmarks. So one such video benchmark is the Core 50 dataset. So this was proposed in 2017 in Coral, and it contains these videos of a person moving different objects around with their hand, right? So you can kind of see there's 10 different object classes across the columns, and each row shows a different object instance, right? So I have like light bulb number 1, light bulb number 2, and etc. So you can kind of create different sequences by structuring these different videos in various ways to test the robustness of your algorithms to various changes in the way that in which the data is being presented. My only qualm with this data set is there's not many classes, there's only 10, and there's only 5 objects per class, right? A couple of years ago, some of my colleagues and I published this data set in a CVPR workshop. So it's called Stream 51, and it kind of took some of this inspiration from the Core 50 video-based data set. So we basically collected videos from existing data sets in the wild, right? So we have images of different animals running around in their natural environment, maybe some vehicles like airplanes taking off at an airport. So you can still simulate those natural or wild environments instead of having these videos of a person moving objects around with their hands, right? And the really unique thing about this data set is we wanted to kind of start moving a little bit away from this closed world supervised learning paradigm where you're training on data, you immediately give testing label, or you give labels for your next batch of data, and then you update that and so on. And so this data set introduces this additional challenge where at test time, the agent not only has to be able to identify those classes that it's learned in the past, right? Like in this first increment, the Fox class, but it also has to be able to label images of things it hasn't seen yet as unknowns, right? So in stage 1, maybe it sees, oh yeah, this is a fox, I know that's a fox, but then it also needs to provide some type of confidence estimate to say, hey, these are classes that are not known yet. And then in the next increment, maybe we give some labels for those horse examples that it was unfamiliar with, and now it has to be able to recognize both foxes and horses while still identifying these other classes as unknown. So this is kind of hinting a bit at what is known as open world learning in the literature, right? So moving beyond what is known as this closed world assumption where we assume that we know all of the classes and we're operating only within that closed set of predefined categories that the agent actually knows. So there's a really nice graphic from this Bendel and Bolt paper from CVPR 2015 that kind of outlines what the open world learning process actually looks like, right? So we move from left to right. Basically on the left, you can see we have a world that has knowns and unknown unknowns, right? So first, the agent has to be able to recognize the knowns, right? These are the things that are within its training distribution that it's seen in the past. It also has to be able to detect things as unknowns. So like I just mentioned, right? Maybe it's seen foxes, but then it doesn't know any other animal and it has to label all of those as unknown with some type of uncertainty score. Then a human annotator or maybe some type of other annotator could come in and label those examples that it detected as unknowns. We now have supervised examples for things it knew and now new things, and it can actually update on those, right? So it's kind of this continual learning process that adds this additional axis of unknowns and uncertainty estimation to it. So you might be asking yourself, what are some of the techniques for being able to identify unknowns, right? So there's two different classes of methods. The first are what are known as inference methods. And these are super cheap. It basically means I have trained up my network. And now at test time, I just want to be able to provide or apply something post hoc to be able to detect what the unknowns are. So basically I can, do something like output layer thresholding. So apply some type of threshold on my softmax scores out of the network to be able to detect what is new versus old. Maybe I could use some type of distance metric. The Mahalanobis distance seems to work really well. So you can basically measure how far samples are from the training distribution of samples it's seen before, things like this. Well, these are super simple to implement in practice. It actually might be interesting to think about how to actually update feature representations using this explicit unknown, right? So not just applying something post hoc, but actually injecting something into the training procedure to be able to understand whether or not my network is understanding what it's learning and being able to provide some uncertainty estimate. So some examples of this are like one verse rest classifiers, a background class regularization method, or even generative models that could maybe tell me if something is falling within or out of my distribution. We published a survey paper on this a couple of years ago, and so this is maybe some graphics from what the different methods look like, but it's kind of interesting to notice the differences across these. Basically, some of these methods do a really good job at understanding exactly what they know and putting those decision boundaries exactly around the things they know and leaving a lot of open space for those things that they don't know. And it's gaining a lot of popularity. You'll actually see a ton of papers on open world learning, even at this ICCV conference. There's tons of citations, and many of these methods are gaining popularity, even in fields like object detection, right? So moving beyond the classification scope and starting to move into harder problems like detection and segmentation and things like this. But beyond open world learning, there's also, let's say that my agent is identifying a bunch of things as unknowns, but maybe it's really costly to annotate all of those unknowns, right? Is there something that we could do that's a little bit smarter so that we don't have to label all of those unknown pieces of data? Is there some way that I could probe my network to ask it, what are the 5 most or 10 most important examples you think to annotate for your performance benefit? And this is basically what we're trying to do with active learning. We're basically having the agent identify those examples that would be the most helpful to label to actually, so that it could actually update on only those, right? And the benefits, obviously, it reduces the compute costs because I'm only now updating on a couple of supervised examples. I guess this is not considering the case where maybe you also update on the unsupervised examples, which would still be just as costly. But it also reduces the annotation cost for human annotators. There's 3 classes of methods for doing active learning. So there's, of course, the simple one, which is just uncertainty heuristics, right? So we could measure the model uncertainty using things like entropy estimations. What are the margins between my class probabilities? Or doing something like ensembling, right? If I have 5 different versions of my model and I can estimate its uncertainty across those 5 different models, is there something in common about what it's with those examples that it has high uncertainty about, right? And doing things like this to better understand those examples that should be annotated. On the flip side, there's also what are known as representation-based approaches. So basically a representation-based approach, imagine I have all of my data in some feature space, and then I want to select examples to cover that entire feature space, right? This is only a possibility if you have the entire training set available to you, right? So you could imagine in an incremental learning setting where maybe I don't know what the future looks like and I don't know what my feature space is going to look like. Maybe these methods don't make as much sense, but still an open question. And the third class of methods are expected error reduction. So basically, for each unlabeled example in my data set, I can compute how much the model predictions would change based on if I had that example included in my annotated set or not. This is super expensive, as you can imagine, right? Because I need to quantify this estimate across all examples in the training data set. And so I've started talking a little bit about some of these considerations, right? So uncertainty heuristics are usually super easy to implement. They don't require all of your data to be available upfront, but they do rely on model uncertainty estimates, right? So you have to have a good estimate of what your model is uncertain about. Representation-based methods are kind of nice because they give you a representative set of your entire feature space, but they do require all of that data to be available to be able to select examples that are representative of the feature space. And I will say expected model change methods are really nice in principle, and I really like to read about them, but they're very computationally expensive and they're often prohibitive in practice. Here's a really nice graphic from this VAL paper that was published in ICCV a couple of years ago. And you can basically see the differences in performance on these two different benchmarks, right? So this variational active learner is in blue, and then we can see maybe a core set or a representation-based approach in orange, and then an ensembling approach in green, right? So you can kind of see some of their differences in performance on these particular benchmarks. So with that, I want to provide some additional resources in case you're super interested on this subject that you could go and read a little bit more about. So there's this really nice paper that I mentioned a bit earlier from Martin Muntz that details continual learning, open set recognition, and active learning all in one paper, right? So it talks about the different methods, what are the differences between these different fields, where can you use them, and things like this. So this is a very nice resource. I highly recommend going and looking at it. If you're more interested in the biological perspective of lifelong learning algorithms, what's biologically plausible? How do we implement regularization that's kind of similar to what's happening in the brain? Things like this. There was a nice paper that was published in Nature Machine Intelligence in 2022 from Dorisha at UT San Antonio. And they detail these different biological underpinnings of lifelong learning. If you want to get your hands dirty, there's this Avalanche library that can be installed using the pip library. So you can just go pip install Avalanche and get yourself going with some of the common benchmarks, some of the most common methods. They're already implemented in there. So this is a really nice tool. And finally, if you want an entire conference that's only on lifelong continual learning, I'm going to pitch this virtual unconference that we're hosting in just a couple of weeks. It's fully online. It's spanning an entire 24-hour period. So basically, anywhere in the world you're located, there's going to be some live talks just for your time zone. It's free, and yeah, I'd really encourage you, if you're interested, to visit our website, get registered. Even if you show up just for 1 or 2 talks, you know, it's still an interesting opportunity. So feel free. And so with that, we've covered a little bit about lifelong learning machines. We've covered what open world learning is and how it relates to continual learning, and also maybe how active learning could be played into the picture. So thank you very much, and I'm happy to take any questions.
Yeah, thanks. Really nice talk. And it also aligns with the previous one. So I have a question that was last one, perhaps. Please say if you want to do out of detection, you can do that in this, right? Go to the if you want to do whatever, like unknown object detection. What would you like to do if you can do like the previous talk, where you do test line adaptation, where you want to receive the test sample, which kind of contradicts the other detection of the technique. Could you do something about it? So that's my question.
Yeah. So this is an interesting question. Basically, we're talking about the difference with the previous talk and how out of distribution detection can relate to test time adaptation. Yeah, so I think this is interesting. I think, as Ricardo mentioned, that the fields are kind of disjoint in the sense that test time adaptation is more about not adapting to new classes, but perhaps adapting to other new changes. So like new domains and things like this, right? So maybe we're not necessarily thinking about updating with new classes at test time, right? Whereas you could still apply some of these out of distribution detection methods to identify new samples or samples that contain new classes, right? So you could kind of marry the fields to be able to update on new domains, but then use out of distribution detection to determine if there's a new class, where I would need to use maybe some type of continual learning method to update with that new class, right? Instead of test time adaptation that doesn't update on new classes. Yeah. I'm not sure. If somebody else knows better than me, maybe let me know. But I think this is a really interesting concept. Yeah. Thank you.
I would like to ask you more about about the field in general. How do you know when to be doing? How do you know when to finish the continual learning process? How possible context here is that is the I learning like as if we have a proven data set is the goal. Do we reach that level of or we hope that we can even better at that?
Yeah, this is a really nice question. So basically you're asking, is the upper bound the IID offline model, or would we expect to do even better? In practice, I think it would be really nice if we could do even better, right? It would basically mean that we're making use of transfer of knowledge, right? Instead of just training from scratch, is there some way that we're actually making use of those previous representations we've learned to learn new data to an even better extent, right? So I think it is possible to go above this upper bound of training offline. But then again, you could restructure your offline training such that you're training in a continual way, right? So maybe then you have an even higher upper bound that's based on this. But yes, I mean, the ultimate goal right now is basically to get as close to that upper bound as we could, but I do think it's possible to go above just standard offline training if we're transferring knowledge in an efficient way such that we can, you know, get some of that carryover to get higher performance. I hope this makes sense. Yeah, thanks.
Hello, thank you for the talk. Just have a fundamental question about active learning. When we are having, let's say, X number of samples, imaging, so to speak, does using active learning lead a better result than using, you know, let's say all these samples? So, or are we just trying to achieve the same result, but with a lesser number of samples?
Yeah, thank you. This is an interesting question, especially in the light of the other one. So basically, it's about what is the upper bound on active learning performance. Yeah, so I mean, even with this question, I think that there might possibly be a way to do better than training with all of the data, especially if I have a lot of anomalous data, right? Like, let's consider that I have a lot of outliers that are maybe not necessarily representative of what my data set actually is. Depending on what my test set contains, if it doesn't contain those outliers, then maybe it's better to only update on a few examples that are falling more in distribution than to update on all of those examples that are falling both in and out of distribution. But this is going to really depend on what your test set looks like too, right?
Thank you.
Yeah, thank you.
The other